We are now discussing basic facts about the Fourier transform in the L1 setting, and also with the pointwise inversion theorem and so on. So the first goal will be to verify that the Riemann Lebesgue Lemma is valid, which means Riemann was, of course, showing that the Fourier coefficients of any Riemann integrable function is tending to infinity. Lebesgue was extending this, of course, to his setting, and nowadays we will say it's the statement that a Fourier transform of an L1 function is not just bounded and continuous, but it's also decaying at infinity. There are different ways of doing it. One approach would be to first verify that the so-called Gauss function is a Fourier invariant function. So for the Gauss function, everything is fine. Then you stretch the Gauss function, you compress it, you approximate a general L1 function by shifted, dilated, modulated, perhaps Gauss functions. And all these procedures leave you in the same space. Now I was checking the different approaches, and what comes now is an approach which is specifically simple for the real line and by product to the general continuous functions. And it's relying on the properties of the boxcar function or its Fourier transform, the so-called SINC function. So we look at general boxcar functions, which are also called, I call them rectangular functions. So they are one on some interval a to b in the real line. So we are for a moment doing one-dimensional stuff. And if you think that you would like to have open intervals, doesn't matter. Even Riemann integrals don't change if you correct the function at finitely many points. So I prefer to take open up closed intervals. Let me check here. And because any interval can be moved to the center, so take the midpoint and shift everything. Shifting a function doesn't change the Fourier transform in absolute values, because shifting a function gives you a phase multiplication on the Fourier transform side. And then we are dilating it so that we can assume that the interval has length 1, which in the symmetric case means it's going from 1/2 to plus 1/2. So the standard or natural box function is the indicator function of the closed interval from -1/2 to plus 1/2. It has integral 1, so L1 norm 1, it's positive, it's symmetric, it's an even function, it has a maximum, of course, of 1. And so we will see that you can compute the Fourier transform by just integrating a cosine function. I've written some details in the notes, which I will send you or provide you, but the point is you integrate, in the sense of complex integrals, a function, again, this boxcar function, against a complex exponential. We all know that by Euler's rule, this is the real part is cosine, imaginary part is sine. The boxcar function is even, so if you multiply it with the odd sine function, you will get an odd function. But if you integrate an odd function, and it's clearly integrable, the part on the negative side will be the minus of the part on the positive side. So the imaginary part of the Fourier integral just disappears due to the symmetry of the function. So we are left with the real part, which is the cosine transform. But this is now an even function. And therefore, we only compute the integral from 0 to 1/2 and then take it twice. Okay, so what is the definite integral of a cosine function? It's just, the inner derivative would be the constant in front of the variable. So it's 1/2 pi s of the sine function. And then you evaluate it at 1/2 or from 0 to 1/2. And that's the integral, which I use already by saying, well, the Fourier transform of this standard boxcar function at S is twice this integral. So it's twice this value, and I insert x equals 1/2 because the sinus function at 0 is just 0. And you're getting the 2 and the 2 cancel out. You're getting a sinus of 2/2 is 1, so it's pi s divided by pi s. And that function is giving the name of the SINC function. Now, strictly speaking, this is not a good definition for s equals 0, because you have 0 divided by 0, and you would expect that this is a troublemaker. But on the other hand, you just insert constant 0, I mean s equals 0, so cosine is 1, so clearly you get the value 1/2 times 2, so it's the value 1, and that's exactly what you would get by de L'Hopital's rule. So you remember, if you want to determine a limit of the form 0 by 0, then you can take the derivatives, and that would be cosine, and that would be constant, so you would get also the value 1. But we know the Fourier transform is a continuous function, so this one value, you just take the limit of those values, and it's a SINC function. Now, we will use the plots of the SINC function quite many times or so, but it's quite clear that you have to expect zeros at every integer except at 0, because at s equals 0, as I said, it is the value 1. And it will go up and down like a sinusoidal function. Now, in the script, you will see a yellow graph where you're doing this by saying, well, in reality, if you take, I don't know, s equals 3.5 or so, then you will see a certain number of full oscillations. They all cancel out. And only the little part from the last not complete period is giving a contribution. This is why you're having this factor 1 to the 2 pi s. So essentially, you're saying instead of having this, you do substitution, you have a long interval, and only a fraction of this is giving a contribution. Also, the up and down is clear because depending on how much of the next integral you get, you may have only a part of the positive part, then it's positive, or you have a dominating part of the negative one, then it's negative. So the SINC function is a function which is continuous, nice zeros at integers minus the identity, but it's not integrable. Now, the main statement of our next discussion is the Riemann Lebesgue Lemma, which states that the Fourier transform of any integrable step, preliminary step, of any integrable step function belongs to C0. Well, actually, it would be enough to say, you give me any step function, and that step function is supposed to consist of finitely many rectangular functions. Let me see if I can find a graph. Yeah, so something like the top function. So that would be a discrete version of a step function. It takes constant values. Of course, for this example, I just took positive values. And for later on, a random piecewise linear function would be not a sum of rectangular functions, but the sum of shifted triangular functions with variable amplitudes. So in this picture, I was taking the same amplitudes to see the large values are the same. And in one case, I took rectangular, in another case, triangular functions. So coming back, the first claim is, if we take such a step function, then the Fourier transform will be also in C0. Clearly, I should say, of course, the SINC function tends to infinity to 0. If you are going with s larger than, let's say, pi s larger than 100, then the values that you can obtain outside are less than 1/100. So this is clearly in C0. Now, we will use them a lot. These dilation operators, which is just dilation in the sense of stretching the graph, or we have the compression operator, which is keeping the area constant. And we will also use quite a bit that the Fourier transform of a compressed function, so something like a Dirac sequence, is just a stretched version of the Fourier transform. So in words is apply, or the other version is you dilate a function, you do a transformation, and you can move it over to the Fourier transform domain, and you get a factor from the transformation matrix. But that just helps you to get from the sinc function to a dilated shift function, and that doesn't change. We have finitely many dilated sinc functions. So if you're working with a very narrow functions, clearly this sinc function will have even very poor decay, but that doesn't matter because we are adding finitely many of them with some amplitudes. On the other hand, if you have the boxcar function not at the origin, then it's just like multiplication with a pure frequency, and that doesn't change the absolute value, so it doesn't change this here. So if you're asking me, what is the Fourier transform of an object that you have seen just now, then I would say take the standard, compress each of these by a dilation operator, then you take a shift, and then you have a finite linear combination. But the Fourier transform is a linear operation. So you're just doing the same thing, and you work from the outside. So translated of something is going to modulate it with a negative modulation factor. Then what's remaining is a dilated version of the boxcar function, which is a compressed or stretched version of the sinc function. And so you have a finite linear combination of objects, each of them, even with coefficients, are in C0. This is a vector space, so all of them are in the C0. Now, the main point of this is when you take an arbitrary, let's say, continuous function, you all know that you can approximate it with step functions. So if you give me any continuous function with compact support, you can approximate it arbitrarily well, even in the uniform sense and even more in the L1 sense, so using the Riemann integrals, by step functions. That's more or less the idea of Riemann's integral. You approximate either from above or from below, or you take arbitrary Riemann sums. They're all very close in the L1 sense to the original one. But the sup norm on the Fourier transform side is at most the same as the L1 norm on the time side. So convergence in L1 gives you uniform convergence of those objects, which are a little bit complicated, but all decaying at infinity. And because the function f is the limit for an arbitrary L1 function is the limit, you get this. So actually, the last sentence is going beyond the statement of the lemma. The lemma was just saying for integrable step function, everything is okay. And I did use already in the proof the Riemann Lebesgue Lemma. Now, the problem with this sinc function, and I have already shown it, is that it's not integrable. Well, in the Riemann sense, it's surprisingly a little bit better because you can take Riemann integrals are not taken globally. You take the limit of the finite sum. So, and then in that way, it might be convergent because the ups and downs are just oscillating, and you can take a limit and then it would be improperly Riemann integrable. But this is like the summability of the alternating harmonic series. So you take 1/2 minus 1/3 plus a quarter minus 1/5 and so on. So this is a sum which is convergent, but if you would reshuffle these terms, it would not be integrable. So we're saying the sinc function is not Lebesgue integrable, and that's kind of a troublemaker. That's why we should look at the triangular function. And I must say, it's just the ordinary situation that you're taking a piecewise linear function starting at -1, going up to the value 1 at the origin. So if you put x equals 0, you have, of course, 1. And then you go down with 1 minus x until you reach the value x equal 1, and then it's 0 again. So you can write it easily as a minimum and maximum. It turned out to be a little bit tricky to do this in GeoGebra, but and then we want to just observe that this is the convolution product of the boxcar function by itself. And therefore, and that's a quite important thing, we have that the Fourier transform of the triangular function, and I use this symbol capital delta for it, is the sinc square function. Now, if we convolve a function with an even function, we can determine the product by taking the pointwise product. So you take the function, flip the second guy, I take twice the same, and the second guy is already flip invariant. So you just take the second rectangle, and then you're integrating over this. But if you take two shifted SINC functions, shifted box functions, if they are far apart from each other, so if they're outside of the interval -1, 1, they will not intersect and the integral will be 0. It's an even function, so the convolution product of two even functions can easily be shown to be even again. So we only have to determine it for y in the positive half interval from 0 to 1. And there it's a slightly shifted rectangular multiplied with a rectangular, and you see it's just the integral of y up to 1 of the constant, which is 1 minus y. So this is how you get that you have the triangular function. Now, I thought it might be interesting to show you, you can do this in GeoGebra yourself, but to show you how this is going into for the case of triangular functions. So how can we convolve triangular function? Oops, sorry. Yeah, I'm showing you this. So I hope you can see it now. So I tried to tell you, I didn't want to do it real time or so, but what I did before was I mean, you can activate this. I'll put it up into a link with the box function. So this was the first part is what I was discussing, is with an if statement. The box function is a 1 if the absolute value of x is less than 1. This is easier to express than saying between -1/2 and 1/2. And also allow to stretch this function. But then take the shifted function, and then I really do this formal definition as we have seen it now. We say you have to integrate the product of the function with the shifted function, because I know everything is 0 outside of -2, 2, actually smaller, but I take a little more. I take this integral, and then you would see the plot of transferring the shift parameter against the value that we have done by computation. Now I decided to do the same thing now with the triangular function. So you see I have already defined the box function, and I was using now this box function to localize the 1 minus x. So this is really, you see, if you're, yeah, this is more or less the triangular function. Now, I call the cubic B-spline, that's the name of the convolution product of the triangular function with the triangular function. You can say also, this is the function which has as a Fourier transform SINC to the fourth power, or it's convolving one more with a rectangular function and convolving one more. So we have associative law, but I thought it's more interesting to show you the GeoGebra experiment to do this. So we compute the integral, which is just the definition of the integral, the triangular function minus the shifted triangular function, and you integrate over the whole support, and you're plotting the point Q. Now, I hope that I was putting trace on, because what I'm doing now is I'm moving the point. So you're shifting, yeah, I'm shifting the point. And you see, depending, it's a bit indoor slow, depending on what parameter I'm choosing, maybe I'm choosing this point, I'm choosing another point, you're getting a curve. Now, I'm not sure if otherwise you have to try to do it. If I would do the animation, it's moving automatically, and because the computation and the transfer takes a little bit time, you're seeing that you're getting a curve. Again, the green curve of all these points Q are vanishing already outside of this interval 0.1, minus 0.1 to plus 0.1. Actually, I think it should vanish outside of only 2. So maybe this just, sorry, it's triangular with triangular is -2 to +2. And you get these values. Now I have done this really in a very naive way, but you see how you get smoothing, and if you stop it, so let's stop the animation. If you go here, you stop the animation. You see here very nicely, maybe I'm going back to the starting point. You see here at the boundary, at some parts, yeah, maybe if you take this here, it's 2 parts of a quadratic polynomial or so. If you move it further out, you're seeing 3 parts. So if you really would compute the integral, as I have done during my PhD thesis, you really have to write quite a few pages. Nowadays, with this GeoGebra, you see that you're actually having a cubic spline function, which means you have a cubic polynomial at each of the segments, -2 to -0.5 and so on. And these cubic polynomials are glued together such that the second derivative is still continuous. So if you take the green path as a roadmap, you can have continuous second derivative, which means continuous change of the curvature, which means if you drive along such a road, the steering wheel that you turn around left and right is moving in a continuous way. It's not like a toy train where you start with a straight line. Maybe you're going like this, and then you're turning with a fixed radius, which would be very disastrous if you would just suddenly turn your wheel by a certain angle or so. So these cubic splines are just much better. Now I'm stopping this here and going back to the screen that we had before. I hope I find my, yeah, maybe, sorry, maybe I'm switching to, because that was GeoGebra. I have another one where I demonstrate the convolution of a rectangular function with a Gauss function. So if you watch it, I hope you can see it, then you will see that the Gauss function is moving inside the graph of this plateau function, which was meant to go from -3 to +3. And you see the resulting curve, which is the blue curve here, is constant 1, a very large part, then it dips down, and so we are just smoothing the edges of the rectangular function with a certain radius. So I'm using that particular Gauss function shown in the middle. Now the standard Gauss function, so the e to the -πx² is showing in the middle. And so what I can do here is I can change the dilation parameter. Maybe I'm making it a little bit broader. So this is just a small compression of the Gauss function. Now I should maybe change this, but you can play around. You see now there is a new blue curve. I should have eliminated it. Maybe I'm doing it. Yeah, so now I'm moving it around. It starts plotting separately. And you see here now this blue curve is not as steep as the old one because my Gauss function is very narrow. So you see that now this is what I'm showing you here is exactly the ST rho operator. So I'm compressing it, and if you make the Gauss function more narrow, as I'm doing it next, so I'm compressing with, let's say, a factor of 3.3, then this new Gauss function is more narrow than the original one, even the one I was showing you before. And that means that the blue curve is now even more steeper. So you can see the effect of convolving two functions. And what we are using also is now that this sequence of more and more compressed Gauss function, they will approximate the rectangular function. And so we have a visual proof that they are an approximate identity. So this is a prototype of a dilated step function. Now, if you would take a very narrow step function, you would look at it at a microscope, your Gauss function would be even more narrow, but in the local description, everything would look fine. And now you should compare the difference in the L1 norm between the rectangular function, this plateau function from -3 to +3, and the blue curve, which is hardly to see because it's already so steep. And you will say, the big part inside the plateau where it's now is harmless and you have zero error. You have a small error in this transition period. Here now it's an error, and that is concentrated on the size of the width of the Gauss function, so it's very narrow. Its maximal deviation is 1, the height of my plateau function, and it's appearing twice on the left and on the right. So this area is shrinking, so that is another way to demonstrate that ST rho of a Gauss function convolved with the plateau function minus the plateau function in the L1 norm goes to 0. We will do this in a more formal way later on, also in the notes. Okay, so I'm going back now, hopefully, to the notes. Yeah, so we have the triangular function is this. Now, I will demonstrate, I show you at another occasion how to do this in the same in MATLAB. There it's important to distinguish between the plots that I'm doing, which should be exactly the plots that you expect from the continuous situation, and the data structure. So maybe I recall to you that such a symmetric rectangular function means symmetric on the unit roots of order n. So the 0 is the value omega to the power 0, which is 1. So it's the furthest east point on the unit circle. And then everything which is going to the right is kind of going up in the circle in the mathematical positive sense. Everything to the left is negative. So these are the last coordinates. So if I take a rectangular filter of n and size 20, it means my n is 480 here. I'm saying, well, I have to put at the first coordinate, which is 0, plus then up to 20 more coordinates. So the first 21 coordinates are 1, and the last 20 coordinates, because these are to the left of 0, the last 20 coordinates are 1. And if I convolve these two guys, I'm getting the triangular function. Now, if you observe, these are really 3 independent plots. I have 1, 1 here, and I get 40, and looking closer, it's 41 here. And it's exactly the convolution product. If you take at 0, you're multiplying those two rectangular functions. Now the discrete integral is a sum, and I have 41 units, so that's why the value is 41. So if I really want to get like partitions of unity of triangular functions, I have to divide through and replace this and make it to a probability measure and say, no, I convolve with this, but divided by the sum of the entries, which is 1 over 41. That's just to tell you. Now, this is the situation similar to the GeoGebra plot. So you would take that as a constant plateau function. This is kind of like a discrete Gauss function, but very nasty. And what you get is constant function inside. Again, value is 41 as long as this guy is moving inside the plateau. When you move to the boundary, it's exactly the phenomenon that you have with the triangular function, and you get the plateau function. So I call this a trapezoidal function if you convolve a big function with a small one. Now, if we go to the Fourier transform domain, we have already seen that this has a Fourier transform which is SINC square. This is a dilated version of a box function, so you will have a product of 2 SINC functions, but at different, so it's not pi s, but it's like 3 pi s or something like this. But overall, it still decays like 1 over x squared, and that means it's integrable. It's even very nicely integrable. So I would like to just show you the picture. The first one, I mean, is showing you the rectangular function has a Fourier transform, which is actually a discrete version of a SINC function. So the spectrum is this. This is a wide, so it's a dilated, and you see that corresponds to compression of this. You also see that it's because it's ordinary stretching, this dilation operator, the area is much bigger, which means the maximal amplitude is much longer. So it's really, it's 201 here. The maximal value is the sum of all these entries. And the oscillation is much more fine. So such pictures will show up in the discussion of the Gibbs phenomenon or so. Now, if you take the convolution product as we have seen of these two guys, you're getting a function which is the product of two things. And this is even better concentrated. So you see the value at the origin is quite big, but it's also decaying very, very much. And so it's much better concentrated. So a piecewise approximation, piecewise linear approximation to a rectangular function is already much more beautiful. And that's why we will work with this function better. Just also to indicate, if you take, that's what I was demonstrating with GeoGebra. If you convolve a triangular function with a triangular function, or you take fourfold convolution, you're getting a broader B-spline. But if you do it further, it's getting, no, I think, sorry, this was convolving triangular with a rectangular function, so you get a piecewise quadratic thing. So you have a quadratic curve here, and you go down. What if you look at this, you can believe that it's C1, it's continuous derivative. So at every point there's a tangent, even at this point where you glue things together, but the second derivative would change, would have a jump at these points here. This is the cubic spline, which is even better. Now, this is SINC squared. This has a Fourier transform SINC third power, which means this guy has also negative values sometimes, like the original SINC function, whereas this is better because it's again positive and decaying very fast, like x to the, or s to the minus 4. Now, this is something that I was doing also with MATLAB, of course, and it's indicating to you something which you can do yourself. So take a histogram of a sum of random variables. You see, I took a large number and then make a fine histogram, and the fine histogram has 100 bins, and I was doing some zoom. Then you see that this histogram is really very similar. It's a triangular shape, and then I was taking the histogram of a sum of 4 random variables. So you see the histogram, if you would take a random number generator, you would see a histogram going from 0 to 1. Now, the histogram of a sum of 2 random variables is going from 0 up to 2, and you see the histogram of 4 would go up to 4. So if you choose 4 random numbers and you add them up, they have a certain distribution. And this plot is just a first and very only visual indication that if you're going to the probability distribution of a random variable and you add 2 random variables, that the sum of the 2 random variables has a distribution which is the same as the convolution product of those 2 sums. Maybe as an indication of where this comes from, think of the experiment with the dice. We all know that the chance for getting a number from 1 to 6 is equal. So it's a fair dice will tell you, I have probability 6 with probability 1/6 for each of the possible outcomes. So assume you're doing an experiment and you're playing the dice 600 times. You would expect that you get, roughly speaking, 100 times each of the possible outcomes. Of course, in reality, if you make a random experiment, you may have 99 in one case, 102 of the other case, and so, but in the histogram, you wouldn't see a very big difference. And of course, you would argue, if you don't take 600, but you take, I don't know, 60,000 or 600,000, your histogram would be much finer, much better. And I would like to tell you, well, this is true because, I mean, what is the probability of getting, I don't know, 4 with 2 dices? So that is the triangular distribution. You can get anything from 2 to 12 with a discrete dice, with a dice. The probability of getting a 1 is the lowest, of course, 2, of course. You get 2 only with probability 1/36, because you get it only when you have the poor outcome of 1 and 1. The same is true for 12, of course. We know it's very rare to get 2 times 6. What is the chance to get a 4? Well, it's the probability of 1 plus 3, or 2 plus 2, or 3 plus 1. So that's already much higher. So which is the outcome, which is the peak and the most likely? Well, it's in the middle between 2 and 12, which is 7. 7 has 6 possibilities. So the outcome 7 with 2 dices is 6 times 1 over 36, which is 1 over 6. So it's like the same probability as getting a 5 with 1 dice or so. And why? Because you can get a 1 plus 6, or 2 plus 5, or 3 plus 4, and so on. So you have exactly 6 different possibilities. And you get this discrete version of a triangular scheme. Now, if you are interested, and that's what I teach in my other teacher classes, so to say, is if you're interested, what is the chance of getting, I don't know, more than 50 points when you're throwing the dice 8 times or so, then you can compute it with MATLAB exactly with this. You just have to take the connection between polynomials, Fourier transforms, and probability or so. So at the moment, it's just probabilities, or probabilities of sums of independent variables are exactly convolutions of the corresponding measures. And again, in the limit, we have a continuous probability distribution, which is, I mean, if you repeat it, you rescale everything, you have a proof of the central limit theorem, and you will say, yes, it's a Gauss curve. And what are you doing normally when you try to find a fit with a normal distribution is to say, I have something like an experimental histogram or experimental probability, which is very, very similar to our deep psi of mu. So if you would take the Fourier transform of those histograms, maybe not with step functions, but with triangular functions, you would see that you would have convergence of the Fourier transforms, but not in the kind of usual sense. You would have large and larger constant behavior as you increase the number of repetitions over large and larger domains. So the low frequency part, the very smooth part, would be very precise already at the very beginning, and then you have to repeat more and more. Now, I have already shown you these step functions and the piecewise linear functions, and to convince you, I have this f2spec command in MATLAB that the step functions have a very poorly concentrated Fourier transform. I show you here the real imaginary part of the Fourier transform of this real value step function compared to the same data, but with piecewise linear approximation. So it's just the behavior between SINC decay and SINC squared decay. Of course, you could try to take a spline approximation with higher order cubic splines or quasi-interpolation, or you smooth your data with a Gauss function, then everything would be much better. These side lobes would disappear and so on. This would be really much better. Now, I think it will take too much time to start GeoGebra. I'm a little bit worried that I'm running out of time. So I would like to tell you how to read this, and you should play around with this, how to read this curve or this plot. So you should take the triangular function. This is the standard triangular function, the convolution square of the boxcar function. And this is a compressed function. And you see here, I have the SINC function. In GeoGebra, you just plug in, you have the SINC square function or so. And so whereas the SINC function is this light brown here, it's going up and a little bit down. You don't see very much. It looks like a decent function, but you have seen step functions have Fourier transforms which are decaying poorly, whereas the SINC square is doing much better. So this is the red curve. And the SINC square is also decaying smaller. So it's decaying, but it's having the zeros at 2 and so on. But it's also the square. We have a dilated Gauss SINC square function. So it's the compressed triangular function, the area preserving compression gives you a dilation of the SINC square function which is probably compressed. Yeah, it's compressed by a factor of 2. That's why I should explain it like this. So this dark gray triangular function is the original compressed by a factor of 2, which means on the Fourier transform side, and that's depicted by the SINC function, I have to do a value preserving dilation with the values being 2. So the original 0 of the SINC square function, which is this one, so that was the SINC square function, is moved from 1 to 2, and the 2 is moved from 2 to 4. So if you would look back, you would see that, but it's cut off. Okay, so in the GeoGebra experiment, you can change the radius, which is the compression radius. You can let the Dirac go to let the triangular function go to the Dirac, and then you will see how the red curve is convergent to the Fourier transform of the Dirac, which is constant 1. And what you will see is that this red curve will get more and more stretched. And let's say this part is already going to infinity, so it will be very close to 1 on a very big domain. Of course, in a finite plot, it's not so easy to plot. See this thing. Now, this is one thing, and the next experiment was then to say, well, now I'm playing around with the shift parameter. So you see here, this is a plot where you can see in the GeoGebra environment, we have the triangular function I call the delta. Yeah, you see here how I have to write it. It's with the signum function. And then you take the dilated version of the delta function. I'm using the Fourier transform, the SINC square function, and I just apply the standard formulas or so. And now the R is the compression ratio, and the A is the shift parameter. So if I take the red curve, which is a very compressed Dirac-like triangular function, and I shift it, it will have an effect on the Fourier transform domain. So making the red function very narrow means on the Fourier transform side, I get this curve, which is the SINC square. We see only the first. So here, probably I was taking a dilation factor of, roughly speaking, so the SINC function is stretched so that the first 0 is at 4 instead of 1. So maybe this is approximately 1/4. But this effect of shifting the red curve to the green curve is giving me an oscillation or so. So we have to understand that there is now one function where we understand perfectly well what the function is. It's a triangular function which you can move around. We know the Fourier transform is the SINC square function. It is integrable. And if we move the Fourier transform, if we move the original function in the time domain, the Fourier transform is modulated or so. Now, if I take this and I go back to the script, I hope this is, yeah, to the script. So that's the original script. We are coming to the so-called fundamental relationship for the Fourier transform. Now, I remember when I was teaching this in a class long ago in the USA, they were saying, oh, professor, how can you integrate a function f hat of y, which is a function of frequency, against a function of time, which is the g of y? And it took me a while to understand what their concern is, the comparison of dimension, but that's why I'm just telling you, well, give me any two nice functions, let's say, or a well-concentrated continuous Riemann integrable function. The Fourier transform will be a bounded continuous function. And of course, you can integrate the product again. The claim is that you can put the hat on either the f or the g. So this looks like a dirty, harmless trick, but it's very useful. And why? Because this is valid for any such function f and any such function g. I'm not sure whether I give an explanation here. No. Yeah, I'm just telling you here, but it's like twice or three times in the script. How you get this? Well, here you have to say, well, what is the Fourier transform? That's an integral over a variable set f of, or maybe I call it x, f of x e to the 2 pi I minus y times x. So both of these integrals are, if you spell them out, are double integrals. Here the integral is first over x, and here the integral is first over y. The first variable is, you have g of y, and you take the Fourier transform in the x variable. So in both cases, you have a product function. Actually, the original versions are f of x times g of y, and you multiply it with the two-dimensional function e to the minus 2 pi I xy. And this, of course, is xy is the same as a yx, and you can change the order of integration. Just think of step functions in R2. The area of a square is, well, a times b or b times a. And if you do this for step functions, you're having the change of integrals of the order of integrals. If you're going further, you are calling it the Fubini integral. So this is true for any possible f. So now the question is, how can we use it to pick out, to recover the function pointwise from the Fourier transform or so? And the idea is quite clear. If you look at this and we say, oh yes, this is very easy. F hat of y is a continuous function, so it's in C0 as we have seen right now. And that's now applying the g as a functional and generate the integral from this. So it's like mu g. So what we have to do to pick out the value, okay, sorry, I should try to go to the other side. Yeah, we have this, but knowing this is the same as knowing the right-hand side, sorry. So now the g hat is again an action on the function f. So how can I get the value, let's say, at x0? You ask me to compute f of x0. And then you will say, well, let's just try to put here a Dirac-like measure. So I would say if this was the Dirac at x0, you would write this as a limit or so. Now, the good thing is we have to understand what does it mean to make the g hat Dirac-like. Well, it means that the g itself has to be something which is very flat and checked and modulated with a pure frequency. So I'm using the pictures that we have seen now with these modulated things and so on. And I will see where I can find now. Yeah, in the script, I'm using the Gauss function, which is also having area 1 to imitate the Dirac measure, but now it would take the triangular function or so. And so to give you an idea, it's a bit, it's maybe too fast, but I will have to finish this lesson for now. I would say, how can I get the value at a given point x? Now the integral is written with a t. I have to compress this d1 row is just my st row, the area preserving. I have to compress the Gauss function or the triangular function in a strong way and shift it to this. So that would be more or less my green guy with area 1 located at the point x. And so this integral, but it would be taking the limit, but that exists and would be exactly f of x. But now using the fundamental relationship, we can change the hats. So instead of f against some function, we take f hat against the Fourier transform. Now the Fourier transform is something, actually I think there should be a minus x, but that I'm not sure, but probably no. This is the Fourier transform. This is the Fourier transform of what it was before. So I have to read this as a Fourier transform, and now we have the d0, which is my ordinary dilation operator, and the modulation operator. So this is this long stretched window, which is having a pure frequency imposed on it, which is the x, which is the frequency here. And that would mean that we have a limit of this relationship, and that's the f hat of 2 pi. So what happens if I integrate the Fourier transform against my strongly stretched version of the SINC squared function. And you would say, well, f hat by the assumption is an integrable function. So you only care for a very big interval where this function is then almost constant 1 times the pure frequency. So we have to establish, if we do it in a formal way, the existence of this integral as a limit of those integrals. So again, approximate your f hat by a compactly supported function and do the job and verify that this limit is justified. Then you use the fundamental relationship, and this is exactly the fact that this is the compressed versions of the triangular function or Gauss functions are a direct sequence, but by the shift it's located at the point where you want to evaluate it. And so we have this very nice and very important formula that if the function is such that f is integrable, so it has a Fourier transform which can be written as an integral, and we have a Fourier transform which is integrable. So nowadays I'm writing f is in L1 intersected FL1 instead of A. Then we have this pointwise relationship f of x equals this integral. Now, in the Lebesgue situation, you have to be even a bit more carefully. Somebody might change your original f within the class or without changing the class on the set of measure 0. So you can take, I don't know, countably many points where you put arbitrary values, and they would not be recovered because they disappear in the Fourier transform. It wouldn't affect the Fourier transform, therefore you cannot hope to recover it. But the good thing is that such a function is well defined. There's only one continuous representative. If you have any L1 function which has one representative which is continuous, then this is the only continuous one. So you would say this inversion formula gives you back the right function. Now, you can already see what is the problem if you want to recover the boxcar function from the SINC function. So f is the boxcar function and the SINC function. This guy would not be integrable. Therefore, at the moment, it's not within our claim. You can, of course, try to recover it, to apply the formula. And in that case, you would find out that you get the value 1/2 at the jump points, and you get the right value 0 outside and 1 inside. So essentially you would say, well, it's a fair compromise. Instead of having the indicator function of the open or the half interval, you get the compromise and the difference between the closed interval, which is +1 at -1/2, +1/2, or at the open interval, which would 0 already at those points is 1/2. But this is a more delicate question, which actually I think is not so relevant for engineers. So questions of pointwise convergence of Fourier transforms is an interesting, mathematically challenging subject, but we will not make use of it. And that's essentially where I would like to stop. So we have now established that Fourier transform can be recovered under some extra conditions, and the function can be recovered from the Fourier transform. Of course, this implies that if f hat is 0, the original function has to be 0. So it's injectivity of the Fourier transform. And furthermore, we will show that it's also isometric on L2. So we will establish Plocherel's theorem also directly from the fundamental relationship. I would like to thank you for your attention, and I will stop the recording now.